Section 1 Introduction. We're here to introduce Code Llama, a new family of large language models, LLMs, designed specifically for code generation and infilling. These models are based on the Llama 2 model and are released under the same permissive license. LLMs are becoming increasingly important in a variety of applications, thanks to their proficiency in natural language. They can be trained to understand and use both general and domain-specific language, making them highly effective in tasks that require advanced language understanding. One of the key areas where LLMs are making a significant impact is in the interaction with computer systems. They can be used for tasks such as generating code from natural language specifications, completing code, debugging, and even generating documentation. Our approach to developing Code Llama involves a series of training and fine-tuning steps to gradually enhance the capabilities of the Llama 2 models. Here's a brief overview of our approach. 1. Code training from foundation models. Unlike other LLMs for code generation that are trained only on code, we start from a foundation model that has been pre-trained on general-purpose text and code data. Our tests show that starting with Llama 2 gives better results than training the same architecture on code alone. 2. Infilling. Traditional training and fine-tuning of LLMs are good for prompt completion, but they don't allow for filling in missing parts of text while considering the full context. Our training for the 7B and 13B Code Llama models includes a multitask objective that combines autoregressive and causal infilling prediction. This allows for applications like real-time completion in source code editors or generating docstrings. 3. Long input contexts. To enable repository-level reasoning for completion or synthesis, we need to provide the model with a much longer context than the 4096 tokens supported by Llama 2. We've added a fine-tuning stage that extends the maximum context length to 100,000 tokens. Our tests show that Code Llama can handle very large contexts with only a moderate impact on performance. 4. Instruction fine-tuning. We've found that the usefulness of LLMs for end users can be significantly improved by fine-tuning the instructions. This also helps to prevent unsafe, toxic, or biased generations. We've further fine-tuned Code Llama instruct variants on a mix of proprietary instruction data and a new machine-generated self-instruct dataset. Our results show that this significantly improves performance on various benchmarks. We've used these approaches to create 3 main variants of Code Llama, each available in 3 sizes: 7B, 13B, and 34B parameters. Code Llama, a foundational model for code generation tasks. Code Llama Python, a version specialized for Python. Code Llama Instruct, a version fine-tuned with human instructions and self-instruct code synthesis data. We've tested our models extensively on major code generation benchmarks, and they've set a new standard among open-source LLMs. We provide all the technical details of our training and fine-tuning procedures, along with in-depth experiments and ablation studies, details of the safety, helpfulness evaluations, and a discussion of related work. Section Summary. In this section, the authors introduce Code Llama, a family of large language models, LLMs, specifically designed for code generation and infilling. Code Llama models are trained on domain-specific datasets and have been shown to outperform models trained solely on code. They also propose techniques to handle long input contexts and improve the utility of LLMs through instruction fine-tuning. The authors provide different variants of Code Llama models, including a foundational model for code generation tasks, a version specialized for Python, and a version fine-tuned with human instructions and self-instruct code synthesis data. Extensive evaluations on code generation benchmarks demonstrate the effectiveness of Code Llama models. Section 2 Code Llama, specializing Llama 2 for code. We're here to introduce Code Llama, a set of foundational models designed for code generation. These models come in 3 sizes: 7 billion, 13 billion, and 34 billion parameters. The 7 billion and 13 billion parameter models are trained with a specific goal in mind, known as the infilling objective. This makes them ideal for use in an integrated development environment, IDE, to complete code in the middle of a file, for instance. The 34 billion parameter model, on the other hand, is trained without this infilling objective. All Code Llama models start with the weights from the Llama 2 model and are trained on a massive dataset of 500 billion tokens, which is heavily focused on code. They are all fine-tuned to handle long contexts, which we'll explain in more detail later. Next, we have the Code Llama Python models, which are specifically designed for generating Python code. They also come in sizes of 7 billion, 13 billion, and 34 billion parameters. These models are created to examine how well models tailored to a single programming language perform compared to models designed for general-purpose code generation. Like the original Code Llama models, these Python-specific models start with the Llama 2 model weights and are trained on the 500 billion token Code Llama dataset. They are then further specialized on an additional 100 billion tokens from a dataset heavily focused on Python. All Code Llama Python models are trained without the infilling objective and are subsequently fine-tuned to handle long contexts. We also have the Code Llama Instruct models, which are based on the original Code Llama models but are fine-tuned with an additional approximately 5 billion tokens to better follow human instructions. Now, let's talk about the dataset we use to train Code Llama. During the initial phase, we train Code Llama on 500 billion tokens, starting from the 7 billion, 13 billion, and 34 billion versions of Llama 2. As shown in our table, Code Llama is trained primarily on a dataset of publicly available code that has been nearly deduplicated. We also source 8% of our sample data from natural language datasets related to code. This dataset contains many discussions about code and code snippets included in natural language questions or answers. To help the model retain natural language understanding skills, we also sample a small proportion of our batches from a natural language dataset. Data is tokenized via byte pair encoding, BPE, using the same tokenizer as Llama and Llama 2. Our preliminary experiments suggest that adding batches sampled from our natural language dataset improves the performance of our models on MBPP. Section Summary. The Code Llama models are foundational models for code generation, available in 3 sizes: 7B, 13B, and 34B parameters. The 7B and 13B models are suitable for completing code in the middle of a file, while the 34B model is trained without the infilling objective. Code Llama Python models are specialized for Python code generation and are further tailored to a single programming language. They are trained on a Python-heavy dataset and fine-tuned to handle long contexts. Code Llama Instruct models are based on Code Llama and fine-tuned with additional tokens to better follow human instructions. The models are trained on a dataset consisting of publicly available code and natural language discussions about code. Section 2.3 Infilling. In this section, we'll discuss 2 key aspects of our research: code infilling and long context fine-tuning. Firstly, let's talk about code infilling. This is the process of predicting missing parts of a program based on the surrounding context. It's a useful tool in many areas, such as code completion in integrated development environments, IDEs, type inference, and generating in code documentation like docstrings. To train our models for this task, we use a method called causal masking. This involves rearranging parts of a training sequence and then predicting the reordered sequence in a step-by-step manner. We've trained our general-purpose models, which have 7 billion and 13 billion parameters respectively, using this infilling objective. To do this, we divide training documents into 3 parts: a prefix, a middle part, and a suffix. The locations of these splits are randomly chosen from a uniform distribution over the document length. We apply this transformation to 90% of documents that aren't split across multiple model contexts. Half of these splits are formatted in a prefix-suffix middle (PSM) format and the other half in a suffix-prefix middle (SPM) format. We've also added 4 special tokens to our tokenizer that mark the start of the prefix, middle part, or suffix, and the end of the infilling span. To ensure consistency between autoregressive and infilling training, we remove the leading space that's usually added when encoding the middle part and the suffix. In the SPM format, we combine the prefix and the middle part before encoding them into tokens. Now, let's move on to long context fine-tuning. This is a key area of research in transformer-based language modeling. The main challenges here are extrapolation, which involves working with sequence lengths beyond those seen during training, and the quadratic complexity of attention passes, which favors training on shorter inputs. For our Code Llama project, we've proposed a dedicated long context fine-tuning stage. Here, models are presented with sequences of 16,384 tokens, a significant increase from the 4,096 tokens used in our initial training stages. This approach allows us to handle longer sequences without significantly increasing training costs. We've also made some changes to the rotary position embedding used in our foundation models. Instead of downscaling frequencies linearly, we've changed the base period from which they're derived. This allows us to process much larger sequences and reduces bias towards short-distance attention. Our experiments have shown that our Code Llama models are not only effective within the increased sequence length used during fine-tuning, but also exhibit stable behavior on very long sequences of up to 100,000 tokens. Section Summary. Code infilling is the task of predicting missing parts of a program based on the surrounding context, and it has applications in code completion, type inference, and generating in code documentation. In this paper, the authors train infilling models using causal masking, where parts of the training sequence are moved to the end and predicted auto-regressively. They also propose a long context fine-tuning stage to handle longer sequences, using a modified rotation frequency of the rotary position embedding to improve long-range capabilities without significantly increasing training costs. Section 2.5 Instruction Fine-Tuning. We've developed a model called Code Llama Instruct, which is an extension of our original Code Llama model. This new model is designed to respond to questions more effectively. To achieve this, we've trained it using 3 distinct types of data. The first type of data comes from a proprietary dataset. This dataset, known as RLHFV5, was initially collected for a project called Llama 2. It was gathered through several rounds of reinforcement learning, using feedback from humans and annotations based on this feedback. The dataset is a mix of thousands of examples from supervised fine-tuning and millions from rejection sampling. Each example is a multi-turn dialogue between a user and an assistant. For the rejection sampling examples, we selected the output from several generations using a reward model. This dataset includes both helpfulness and safety data, which allows Code Llama Instruct to adopt the instruction following and safety features of Llama 2. The second type of data is what we call self-instruct. Our proprietary dataset doesn't have many examples of code-related tasks. Gathering supervised data from human annotators or training from human feedback is costly for coding tasks because it requires input from professional developers. So, instead of human feedback, we use execution feedback to select data for training our model. We've created a self-instruction dataset using the following steps, which resulted in approximately 14,000 question test solution triplets. 1. We generated 62,000 interview-style programming questions using Llama 270B. 2. We removed exact duplicates from the set of questions, leaving us with about 52,000 questions. 3. For each question, we did the following. A. Generated unit tests using Code Llama 7B. B. Generated 10 Python solutions using Code Llama 7B. Circa ran the unit tests on the 10 solutions. We added the first solution that passed the tests, along with its corresponding question and tests, to the self-instruct dataset. We used Code Llama 7B to generate the tests and Python solutions because we found it more efficient than generating fewer solutions per question with the 34B model for the same compute budget. The third type of data is called rehearsal. To ensure that Code Llama Instruct doesn't lose its general coding and language understanding capabilities, we also trained it with a small amount of data from the code dataset, 6%, and our natural language dataset, 2%. Section Summary. The instruction fine-tuned models, Code Llama Instruct, are trained on a proprietary dataset and a self-instruction dataset. The proprietary dataset consists of multi-turn dialogues between a user and an assistant, collected through reinforcement learning and human feedback annotation. The self-instruction dataset is generated by prompting Llama 2 with programming questions, generating unit tests and Python solutions, and selecting the first solution that passes the tests. Additionally, a small proportion of data from the code dataset and natural language dataset is included in the training to prevent regression on general coding and language understanding capabilities. Section: Optimization. Let's talk about optimization. We've chosen to use the Atom W optimizer, with beta_1 and beta_2 values set at 0.9 and 0.95 respectively. We've also implemented a cosine schedule with a warm-up phase of 1,000 steps, and we've decided to set the final learning rate to be 1/30th of the peak learning rate. Our batch size is 4 million tokens, which we present in sequences of 4,096 tokens each. Interestingly, we've found that contrary to the usual practice of using lower learning rates during the fine-tuning stages than in the pre-training stages, we actually achieved the best results when we maintained the original learning rate of the Llama 2 base model. We've applied these findings to our 13 billion and 34 billion models, setting their learning rates to 0.0003 and 0.00015 respectively. For Python fine-tuning, we've set the initial learning rate to 0.0001. For Code Llama Instruct, we train with a batch size of 524,288 tokens and on approximately 5 billion tokens in total. Now, let's discuss long context fine-tuning. For this, we use a learning rate of 0.00002, a sequence length of 16,384, and reset rope frequencies with a base value of 1 million. The batch size is set to 2 million tokens for model sizes 7 billion and 13 billion and to 1 million tokens for model size 34 billion. Training typically lasts for 10,000 gradient steps. However, we noticed some instabilities in downstream performance for certain configurations, so we adjusted the number of gradient steps to 11,000 for the 34 billion models and to 3,000 for code Llama 7 billion. Let's move on to the results. We've tested our models on a variety of benchmarks. First, we evaluated them on popular description to code generation benchmarks for Python, such as Human Eval, MBPP, and apps. We also tested our models on other programming languages using multi-PLE, including C++, Java, PHP, C#, TypeScript, and Bash. Additionally, we reported results on the GSM-8K benchmark, which measures mathematical reasoning capabilities. We also conducted an extensive ablation study. We examined the impact of training from scratch or from a pre-trained Llama 2 model. We performed ablations for infilling and additional infilling-specific benchmarks. We studied the effect of long context fine-tuning on perplexity, a synthetic retrieval task, and code completion with long source code files. Finally, we evaluated our instruction fine-tuning procedure, which includes self-instruct training by leveraging self-generated unit tests. Section summary. The optimization process for our models involves using the Atom W optimizer with specific beta values, a cosine schedule with warm-up steps, and a batch size of 4M tokens. We found that retaining the original learning rate from the base model yielded the best results, and we applied this learning rate to the 13B and 34B models as well. For long context fine-tuning, we used a learning rate of 2e⁻⁻5, a sequence length of 16,384, and specific batch sizes for different model sizes. We evaluated our models on various benchmarks, including description to code generation for Python and other programming languages, as well as mathematical reasoning capabilities. We also conducted an extensive ablation study to analyze different training approaches and their impact on performance. Section 3.1.1 Python Code Generation. Let's delve into the results of Python code generation using three benchmarks: Human Eval, MBPP, and apps. We've found some interesting insights that we'd like to share with you. Firstly, we've discovered the importance of model specialization. By comparing Llama 2, Code Llama, and Code Llama Python, we've noticed that specializing a model can significantly enhance its code generation capabilities. For instance, Llama 2 was trained on 2 trillion tokens, but by adding an extra 500 billion tokens from a code-heavy dataset, we saw a substantial improvement in performance on both Human Eval and MBPP. This improvement was so significant that Llama 2 with 70 billion parameters performed almost as well as Code Llama with 7 billion parameters on Python coding benchmarks. We also found that training Code Llama on an additional 100 billion tokens from a Python-heavy dataset led to considerable gains on Python code generation benchmarks. These gains ranged from 4.3% to 8.3% in Human Eval pass at 1 and from 1.2% to 6.4% in MBPP pass at 1. Although these gains were smaller than the first code training step, they still allowed Code Llama Python with 7 billion parameters to outperform even Code Llama with 13 billion parameters on MBPP and Human Eval. However, when it came to the apps benchmark, which has more complex and less direct prompts than MBPP and Human Eval, our Code Llama Python models showed a slight decrease in performance on introductory and interview-level problems. These problems often require a better understanding of the prompt, which can be more challenging for a language model than implementing a solution. Despite this, Code Llama Python showed clear improvements on competition-level problems, which have more complex solutions. While large language models can learn to generate text on various topics, we found that model specialization is beneficial for models with between 7 billion and 34 billion parameters and after 2 full epochs on the training data. Secondly, we've observed that the size of the model matters when it comes to specialized models. Larger models consistently outperformed their smaller counterparts on almost every metric from Human Eval, MBPP, and apps. For example, we saw a 5.6% improvement on MBPP pass at 1 when we increased the parameters of Code Llama from 7 billion to 13 billion, and an additional 8% improvement when we increased it to 34 billion. This suggests that specializing larger models for coding could lead to significant further improvements on coding tasks. Furthermore, the chinchilla scaling laws suggest that larger models would benefit more from training on more tokens. Section summary. The authors report their findings on Python code generation using various benchmarks. They observe that model specialization significantly improves code generation capabilities, with even small increases in training data resulting in substantial performance gains. Scaling the number of parameters also proves to be beneficial, as larger models outperform their smaller counterparts on multiple metrics, suggesting that further gains can be achieved by specializing larger models to coding tasks. Section 3.1.2 Multilingual Evaluation. In this section, we'll be discussing our evaluation of our models across a variety of programming languages. We used the Multiple benchmark for this purpose, and we tested our models on Python, C++, Java, PHP, TypeScript, C#, and Bash. The results are presented in a table. We noticed that our Code Llama models consistently outperformed the Llama 2 models, regardless of the programming language. This improvement was similar to what we observed in our Python evaluation. In fact, our Code Llama 7b model even surpassed the performance of the larger Llama 270b model. When compared to other models that are publicly available, ours showed particular strength in a multilingual setting. For instance, Code Llama 7b outperformed larger models like CodeGen Multi and StarCoder, and matched the performance of Codex. We also compared the performance of Code Llama Python to that of Code Llama. While Code Llama Python 30b performed slightly worse than Code Llama, the 7b and 13b versions of Code Llama Python actually performed slightly better than their counterparts without Python fine-tuning. To better understand the impact of multilingual pre-training, we measured the correlations between each of the evaluated languages. We found a high correlation between model performance on C++, C#, Java, and PHP. Interestingly, we also noticed a strong correlation between model performance on Python and Bash. As expected, the larger and more expressive the models, the higher the correlation between the performance across all different languages. We also evaluated the performance cost of infilling training. Previous studies on infilling code models suggested that the traditional next token prediction objective could be replaced by a multitask infilling objective with an infilling rate of up to 90% without significantly impacting left or right autoregressive test losses and only slightly affecting downstream evaluation performance. We independently validated these findings using models with 7b and 13b parameters and 500b training tokens of code. The 7b model experienced a slight drop in performance, losing 0.6 percentage points on average across human eval and MBPP pass at 1, pass at 10, and pass at 100 scores when trained with an infilling objective. The 13b model saw a slightly larger drop, losing 1.1 percentage points. Despite this slight decrease in performance, we decided to release Code Llama 7b and 13b in this configuration due to the broad applicability of models with infilling capability. Section Summary. The authors evaluate their models on a diverse set of programming languages using the Multiple benchmark and find that the Code Llama models outperform the Llama 2 models in code generation across different languages. They also observe high correlations between model performance on certain languages, such as C++, C#, Java, PHP, Python, and Bash. Additionally, the authors validate previous findings that infilling training has a modest decline in performance, leading them to release Code Llama 7b and 13b models with infilling capability. Section. Code Infilling Benchmarks. We've been working on models that fill in missing parts of code, and we're proud to say that they're among the best in their class. We've tested them on two benchmarks that are based on the human eval benchmark. The first benchmark takes the reference solutions from the human eval benchmark and turns them into infilling problems. This is done by hiding either individual lines or blocks of multiple consecutive lines. This benchmark was later expanded to include a task where the hiding is done at the character level on a randomly selected substring. The model's predictions are then scored based on the original human eval problem's test cases. Our models have performed exceptionally well, outdoing all other models of the same size. However, we did notice that the results were significantly worse when the format was suffix-prefix middle, SPM, rather than prefix-suffix middle, PSM. This is because the SPM format requires a process called token healing, which we didn't implement for this evaluation. The second benchmark translates the human eval infilling benchmark into other programming languages. Here, single lines are hidden and the model's predictions are scored based on how well they match the correct solution. Our models, including Code Llama 7b, outperformed all other models across the three programming languages in the benchmark. We also noticed that the performance improved when we used the SPM format. We also tested CodeLlama's ability to work with long sequences. We measured its perplexity, key retrieval accuracy, and performance during generation on code completion tasks. In terms of perplexity, We calculated it over 4 million tokens from the code dataset, using a subset of our validation data that consisted of large source files. We found that the perplexity decreased steadily well beyond 16,384 tokens, which is the sequence length we use for long context fine-tuning. After 100,000 tokens, the perplexity only increased slightly, which is a contrast to the instability often seen when testing transformer models on larger sequences. For key retrieval, we tested the model's performance in a synthetic task. The task involved a large amount of valid Python code, with a function returning a scalar inserted at a specific position. The model was then asked to complete an assert statement with the return value of the inserted function. All models performed well on the sequence length they were trained on, except for the 7B model when the function was placed at the beginning of the prompt. For sequences beyond 16,000 tokens, our models showed a decrease in performance. However, we're still proud of their performance and are excited to continue improving them. Section Summary. The paper discusses code infilling benchmarks and evaluates the performance of infilling models on these benchmarks. The models achieve state-of-the-art results and outperform other models of their size. The paper also explores the ability of the models to work with long sequences, measuring perplexity and key retrieval accuracy, and observes positive results in both areas. Section: Single-line completion. Let's delve into the topic of single-line code completion. We wanted to see how well our models could handle long context sizes in this task. To do this, we used the long code completion (LCC) benchmark as our testing ground. It's important to note that the LCC data points were part of our training data. The LCC test set tends to favor shorter files, so we decided to create a new set of examples from the LCC's validation and test set, ensuring an equal distribution over file size. We then compared the accuracy of our code Llama models to their previous versions before they were fine-tuned for long context. The models that weren't fine-tuned for long context struggled to generate meaningful completions on long sequences. To address this, we limited their prompts to the 4,000 tokens immediately preceding the line to complete. The results were clear. Models fine-tuned to handle long contexts performed significantly better. This shows that long contexts are valuable for code completion, and our models can use this information to improve their output. In fact, even in the longest example prompt in this test, which consisted of 103,000 tokens, all code Llama models were able to generate syntactically correct completions. The 7B model even produced an exact match. However, we did notice that while our models are effective on long sequences, fine-tuning for long context slightly reduced performance on standard code synthesis benchmarks that consist of short sequences. We saw an average decrease of 0.52 percentage points on human eval pass at 1 and 1.9 points on MBPP for the pass at 1 metric. When we looked at the code completion results by the number of tokens in each example, we found that for prompts shorter than 4,000 tokens, long context fine-tuning led to a reduction of up to 2 blue points from base models after code training. We saw similar decreases in performance for infilling tasks. While fine-tuning for long context does come with a cost for short sequences, and slightly lowers our scores on standard coding benchmarks like human eval and MBPP, we believe the benefits outweigh the drawbacks. Many real-world use cases aren't captured by these benchmarks, and the ability to handle long sequences is crucial for real downstream applications. That's why we've decided to release all our code Llama Python, and code Llama Instruct models with long context capabilities. Now, let's talk about fine-tuning Llama 2 versus training from scratch on code. Code Llama is based on the Llama 2 models, which were trained on 2 trillion tokens of text, including only 80 billion tokens of code. We fine-tuned these models on an additional 500 billion tokens, 85% of which were code. When we compared the 7B parameters model to an identical model trained from scratch on the same data mix, we found that at the end of training, the loss of the model trained from scratch was equal to the loss of code Llama 7B at about half of its training, even though it had 240 billion fewer training tokens. Moreover, this gap increased over time. Section Summary. In this section, the authors test the benefits of handling long context sizes in a code completion task. They compare the completion accuracy of models before and after fine-tuning for long contexts and find that models fine-tuned for long contexts achieve significantly higher performance. However, they also observe a slight decrease in performance on standard code synthesis benchmarks consisting of short sequences. Despite this, they believe that the potential of handling long sequences outweighs this cost and choose to release their models with long context capabilities. Section: General helpfulness versus coding ability. We're going to delve into the comparison between Code Llama Instruct and Llama 2 Chat, focusing on their coding capabilities and overall helpfulness. We've found that Code Llama not only enhances its coding skills with each model size but also maintains the general helpfulness performance that it inherited from Llama 2. This suggests that Code Llama is highly effective at following general instructions. However, we should be cautious with these results, as our automatic evaluation was limited to scoring the model's responses using the Llama 2 reward model. Next, we'll discuss the importance of self-instruct data, which we generate using our own model. To assess the model's ability to answer questions, we use a zero-shot version of MBPP. We prompt the model to generate code within Python and Python tags, making it easier to parse the result. The exact prompt we use is shown in a figure in the appendix. The impact of training on data generated using our models and filtered with unit tests is shown in a table. This self-instruct data helps us improve our scores on benchmarks like human eval and MBPP, and it also makes the training process more reliable. With self-instruct, the model can easily learn to follow the format requested for MBPP zero-shot, whereas it sometimes struggles without it. For comparison, we also fine-tuned Code Llama Python 34B on 15,000 unnatural instructions, using the same prompts as for the self-instruct dataset. Although we're not releasing this model, we've noticed significant improvements on human eval and MBPP, suggesting that substantial progress can be made with a small set of high-quality coding data. The results of this unnatural model are shown in a table. Lastly, we'll look at the pass at K evaluation. We examined the impact of the sampling temperature on the pass at K performance, specifically reporting pass at 1, 10, and 100 using temperatures of 0.1, 0.4, 0.6, and 0.8 on both human eval and MBPP. The results, shown in a figure, indicate that as we increase the temperature, the pass at 1 scores decrease, while the pass at 10 and pass at 100 scores improve.